Hello and welcome to module 7 on source coding. Let us start with a brief outline of today's talk. We will discuss the practical applications of source coding and we will start with an optimal quantizer. We will discuss about entropy rate and then finally some practical applications of source coding leading to JPEG compression, and of course we will look at some examples. So, that is the roadmap for today. We begin by a quick recap. We have already done Huffman coding, which gives us a prefix code. We saw arithmetic coding, how it is done, how it is better than Huffman coding because we go on the real line between 0 and 1. But both Huffman coding and arithmetic coding require the input probabilities a priori. If we do not have the input probabilities both at the transmission side and the receiving side, we are in trouble. Lempel-Ziv coding on the other hand does not require you to have the measurement or estimate of the input probabilities before you start encoding. So, that is the good part. We also looked at this notion of run length coding. What is a run? It is a long sequence of 1 or a long sequence of zeros. These are typically found in fax data or in images or sometimes in peculiar encoding that is required to be done. So, run length coding takes care of these long runs of 1s and zeros, in which you pretty much encode how many of what. Okay, that is the basic idea behind run length coding, and we looked at some examples in the last class. Now, let us look at an optimum quantizer design. This is a practical problem and we would see how the concept of source coding can be applied here. So, let us consider a continuous amplitude signal whose amplitude is to be quantized, but this amplitude is not uniformly distributed. Is this a good assumption? Well, in many real life cases this happens to be true. Even if I take my speech or I measure the vibrations of a bridge, most likely the amplitude is distributed closer to the mean value and the very high or very low values on either side of 0 happens rarely. So, let us have this continuous amplitude signal whose amplitude is not uniformly distributed. We also know something else. The probability density function of this amplitude varies and it is given by p of x. Now, we wish to design an optimum scalar quantizer that minimizes some function of the quantization error. Okay? So, quantization error q is x tilde minus x, where x tilde is the quantized value of x. Now, we define the distortion as d, it is integrated from minus infinity to infinity, some function of x tilde minus x. So, this is the kind of quantization error, f is the function of that, weighted with the probability distribution of the amplitude p of x d of x. Fine. So, I can have any function of a properly defined function f of x tilde minus x. Now, an optimum quantizer is one that minimizes d by optimally selecting the output levels and the corresponding input range of each output level. Basically, that is the problem of a quantizer design. So, if you do not want to do any of this hard work, you have a uniform quantizer, but that is clearly not going to solve our problem correctly because the amplitude itself is non-uniformly distributed. So, this kind of a problem was first formulated by Lloyd Max and it is called the Lloyd Max quantizer. Now, suppose we have L levels of this quantizer. The distortion is simply given by d equal to summation over all the levels k is equal to 1 through L, and then I have this integration, okay, of f of this quantization error xk tilde minus x. So, this time it is xk, okay, and weighted by px dx. So, the necessary conditions for minimum distortion are obtained by differentiating d with respect to xk and xk tilde, and if you do that basic math, you will come up with a condition that f xk tilde minus xk is equal to f xk plus 1 tilde minus xk for k is equal to 1 to up to L minus 1, right. And then if you take a special case of mean square error. So, I want to design an optimum quantizer that minimizes the mean square error. It is a good function to take. You come up with these levels, the quantization levels xk given as xk tilde plus xk plus 1 tilde by 2. And we have this condition that xk tilde minus x px dx integration over one interval is equal to 0. So, this is just an example of how you solve it, but the question is now how do we fit in source coding here. So, this non-uniform quantizers are optimized with respect to distortion, that is what we have done. So, we have defined a distortion measure and we have optimized according to that. But the question is each quantized sample is represented by equal number of bits. So far what we have done is broken up the total range of the amplitude into quantization levels, but then suppose there are 8 quantization levels, we would put 3 bits per sample. But that is not clearly the best way to do things, because of the px, the amplitude distribution, all quantization levels are not equally likely. So, I will treat the quantization levels as symbols. They are not equally likely, just like my example earlier. Suppose I am talking and my voice is being recorded, I will have probably more samples closer to the mean value and I scream only once in a while. So, very high values are taken very rarely. So, what we do is we would like to have a more efficient variable length coding for this optimum quantizer, which was optimized for the distortion measure. And these probabilities are then used to design the efficient variable length code, therefore, the source coding. So, quantization itself is a compression to begin with. Why? I have this continuous signal and it has infinite information content. Take any sample and you should require infinite number of bits to quantize and represent it. But the moment we quantize it, we have a finite number of bits. The number of levels of the quantizer actually decides how many bits per sample. But we are not content with that. What we would like to further do is understand that different samples occur with different probabilities, and we will do Huffman coding on that. All right. So, let us look at an example. So, we have 8 level quantizers, but my amplitude is not uniformly distributed, and therefore, I have a simple xk which tells me how I have distributed my levels. So, if you look at this graphically, so you have this amplitude and you have this quantization levels. So, you can have 0 and you have 0.5 as one level and minus 0.5 as these two levels, and then you do not have exactly at 1, but you have at 1.05 the next level. Had it been a uniform quantizer, I probably should have equal lengths, and here I have minus 1.05. This is my somewhere here minus 1.05. Right. So, now if we can just redraw this, so that there is not much scope for confusion. So, we have an amplitude and I have got 0.5 minus 0.5 and then we have 1.05 and then minus 1.05. And then we do not go up to 1.5, we go right up and we have this 1.748 and then we again here have minus 1.748. Okay. So, we have these kind of quantization levels which we can define and so forth. Now, please note that if you look at this table, the P of x, Pxk, you have different probabilities associated with the different levels. Okay. Clearly, it means that level 0 and level 0.5, okay, they are almost close to 20% probable. So, 0.19 is a probability of occurrence. So, 40% of my time my signal is captured by these two levels. But then as we move away, yes, I get low signal values and very high signal values with lower probabilities and even higher with even less probability. Okay. So, clearly I have got a range of probabilities associated with different levels, and it should not stop me from forming the Huffman code, which is giving as the last column, and I have represented the more frequently occurring levels, quantization values, as with fewer number of bits as opposed to the rarely occurring very high and very low values. So, level 1, if you would like to call it compression, happened when I quantized it. The infinite number of bits which was supposed to be used to represent a continuous random variable got represented with finite number of bits. But here in this case, ideally I should have had 3 bits per every level, but looking at the different probabilities, I have put a more efficient Huffman code. Okay. Just to complete this example, we have now a distortion value d is equal to 0.0345, which is can be represented in terms of dBs minus 14.62 dB. So, you can compare two different quantizers with respect to their distortions. If I have defined mean square error and two people are selling you two quantizers, you can calculate the distortions with respect to mean square error and then choose to buy any one. Now, clearly we did not go for r is equal to 3 bits per symbol. We chose not to have equal number of bits per level, and since we did Huffman coding, we ended up having 2.88 bits per sample as opposed to 3. And of course, if you look at this P of x and calculate the theoretical limit, it tells you that it is 2.82 bits per sample that I could have achieved the best. It is not in my control. In this practical scenario, I can at best give you 2.88 bits per sample on an average. So, that is the 3 most critical words, on an average. It is not just if you just pick up, it is my bad day and a very high value of the sample comes in, of course, I am spending 4 bits per symbol. Another high value sample comes in, again I end up spending 4 bits. But then the law of averages will take over, sooner or later I will start getting values closer to the mean, and then I will have 2 bits per symbol and so on and so forth, and the average out will be roughly 2.88. So, this is an example where we have been able to use source coding to reduce the bits per sample to be sent. Now we change gears and we talk about something called as entropy rate. Now we observed in the last class when we talked about using blocks for coding and trying to achieve the source code theoretical limit, we observed that a simple extension of the source coding theorem is that n h of x bits are sufficient on an average to describe n independent and identically distributed random variables, each with entropy h of x. Okay? It is just very intuitive. But in real world we do encounter random variables that are dependent. And the question is, what if the random variables form a stationary process? We do encounter that quite a bit in electrical engineering. So how do we define the corresponding entropy for that? Do we have a different measure? So let us define a stochastic process is said to be stationary if the joint distribution of any subset of the sequence of random variables is invariant with respect to shifts in the time index. So, I have seen this definition earlier, but we put it again together, and here this lambda is actually dot dot dot. So, we have x 1 is equal to x 1, capital X 2 is equal to x 2, dot 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 up to x n equal to x n, right, is given there for every shift m. So, I have shifted the indices 1 plus m, 2 plus m, n plus m, and therefore, this kind of a definition tells us that the stochastic process is indeed stationary. Okay. Now, we go a little bit further and we define what is a Markov process or a Markov chain. So, a discrete stochastic process x 1 x 2 dot dot dot, so it can go up to infinity, is said to be a Markov chain or a Markov process if for n is equal to 1 2 dot dot dot, so it can go up to infinity, is defined as the conditional probability p x n plus 1 should be equal to x n plus 1 given all the previous ones is nothing but the conditional probability p x n plus 1 given x n. That is, it just depends on the previous sample for all x 1, x 2 dot 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 up to x n. Therefore, the probability density function of a Markov process can be written as p x 1 x 2, this is dot 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 up to x n, is nothing but p x 1 times p x 2 given x 1, but rest do not matter, times p x 3 given x 2, the rest do not matter, dot 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 up to x n given x n minus 1. So, that is the beauty of a Markov process. So, why are we talking about Markov process all of a sudden? We will connect it quickly. If we have a sequence of n random variables, please note a sequence of n random variables, it is interesting to explore how the entropy of the sequence grows with n. So, it is a question we have posed to ourselves. So, entropy rate is used to define the rate of growth. So, let us understand the physical significance. We have a sequence of random variables, okay, and they are not independent, they are dependent. Okay. So, the occurrence of each one probably depends on the previous one and possibly the previous to previous one, and so on and so forth. Now, they are random variables, they are dependent, so there is an entropy associated with it. But I let this sequence play along, and as n increases, how do you define this rate of growth? So, we define it. The entropy rate of a stochastic process x is given by h of x, where limit n tends to infinity normalized by 1 over n, h x x 1 x 2 dot 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 up to x n, provided the limit exists. So, it is possible that the limit may not exist. So, what do we already know? We know h joint entropy h of x 1 comma x 2 dot 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 up to x n. right. What are these n? These are this n random variables. So, we are talking about the joint entropy, and I have normalized it with n, and I am letting this n tend to infinity. If this quantity exists, that is defined as the entropy rate. Okay. So, this thing has an equivalent definition for stationary Markov chain. So, we know stationarity, we know Markov chain. So, for stationary Markov chain, the entropy rate is given by h of x, again limit n tends to infinity x n given x n minus 1 dot 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 up to x 1, and that can be simplified as n tends to infinity limit x n given x n minus 1 is simply equal to h x 2 given x 1 using the properties of the Markov chain. So, let us look at a simple example. So, let us consider a two state Markov chain with the probability transition matrix such that I have got state 1 by the red dot, state 2 by the blue dot. So, this state transitions into the blue dot with probability p 1, and it goes back to red dot with probability p 2, and sometimes it stays as it is with probability 1 minus p 2. Similarly, the red dot stays back with probability 1 minus p 1. So, this is a simple state diagram of a two state Markov chain. They are fairly easy to understand this one. So, for stationary distribution, the net probability distribution across any cut set in the state transition graph should be 0, that is a standard definition. So, let alpha and beta be the stationary probabilities of the two states. What are we talking about? Well, what is the probability of being in red or the probability of being in the blue state? Okay. That can be written as alpha is equal to p 2 over p 1 plus p 2 is the distribution, stationary distribution for alpha being the probability of state red, and similarly beta is p 1 over p 1 plus p 2. Now, it does not require too much thinking to note that alpha plus beta should be 1. I should be either in state red or in state blue, but there is a probability of being in red and the probability of being in blue, and they keep flipping with certain probabilities. It switches back and forth, sometimes it does not switch, and therefore, I can determine what is the probability of being in state 1 and state 2. And looking at the definition, you have the h of x n, the entropy for state x n at any time n can be written as, well, there are only two possibilities. So, it is like tossing of the coin, sometimes head comes, sometimes tail comes, sometimes in alpha, sometimes I am in state blue, sometimes in state red. So, alpha and beta are the probabilities, and I get h of alpha comma beta, right. So, if you want to find out the entropy rate of this two state Markov chain, it is given by h x is h of x 2 given x 1, right, is the weighted probability. So, p 2 over p 1 plus p 2, which is nothing but alpha. So, I have got alpha h p 1 plus beta h p 2. So, this is a simple example of how you can apply your concepts to entropy rate, and you can define it. So, you could have 3 state, 4 state up to n state Markov process. All right. So, now we come to a practical application of source coding. We have already looked at the optimum quantizer, but now let us look at a more widespread application which touches our lives almost on a daily basis. Whenever we download an image on our mobile phone or send a picture to our friend, we most likely are using some kind of an image compression technique, and one of the most commonly used one is the JPEG, which stands for Joint Photographic Experts Group. So, even though it is almost a de facto standard. It's commonly used. There are other JPEG standards available today, but JPEG is an image compression standard de facto, which is actually a description of several 25 distinct coding systems. Why there are so many approaches? Because the needs of the users vary a lot with respect to the quality, compression and computation time. So, JPEG permits the user to probably have a poorer quality image which is compressed, but requires lesser time and uses fewer number of bits. But let us describe two methods that we have studied which are used in JPEG compression standard. So, the two techniques that we have looked at are Huffman coding and arithmetic coding. Okay. So, some compression can be achieved if we can predict the next pixel using the previous pixel, and this kind of a differential coding is also used. Now, please note JPEG has two kinds of compression built into it. One is lossy, where we lose information, and one is lossless, where we can completely reconstruct the image, the original image from the compressed image without any loss of data. So, we will talk briefly about both of them. So, what are we going to explore in the next few slides? We are looking at how lossy compression works, how lossless compression works, and how differential coding is used to our advantage in JPEG compression. So, let us look at the nuts and bolts, the basic building blocks. The JPEG compression uses something called discrete cosine transform. Just as Fourier transform takes you from say time domain to frequency domain or spatial domain to spatial frequency domain, similarly DCT takes you from the spatial domain to the spatial frequency domain. So, it is defined as follows. So, there is a double summation, and then Yij is the spatial domain and capital YKL represents the spatial frequency domain. Now, please note this is a real transform. It also does the job similar to Fourier, but it is a real transform, and in images we would rather work with real transforms because we would not like to put in additional effort to handle complex numbers. So, all DCT multiplications are real, right. So, this lowers the number of required multiplications as compared to discrete Fourier transform. But why do we use this DCT? What is so great about it? Well, for most real world images, most of the signal energy lies at the low frequency, okay, which appears at the upper left corner of the DCT. The lower right values represent the higher frequency and often small values. So, let us understand this a little better. Suppose we have a standard image. Okay. So, you can have anything that you would like, any standard image. Okay. Now, if we take the DCT, it will also give you another matrix. Okay. But this is in spatial frequency domain. We are comfortable with time and frequency, here we have space and frequency. Okay. So, just as we have x and y, okay, we can have here k and l, but in some sense this k may correspond to the spatial frequency along the x, and this L may correspond to the spatial frequency along y. Now, if you look at this, this is the low frequency and this is the high frequency. Again, this is the low, and going down, this is the high, and of course this is high and high. This guy is the DC part. So, the first value is nothing but the average of all the pixels taken. So, add them up and divide by the total number of pixels, and you get this DC value. Rest all of the coefficients are the AC coefficients. Now, why DCT? If there is fair amount of correlation in this original image, then maximum energy is compartmentalized in the lower terms. So, here, 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 here. What does it mean? Please note, this side represents low frequency. As we go along this axis, it represents high frequency, but of what? Dealing with x. If we go along this side, the same is along y, and if there is high frequency, spatial frequency, then you have high values here. But we live in a real world, inertia dominates, things do not change very frequently, and so there is a lot of correlation within the image. And if the input image is highly correlated, then DCT does a great job of concentrating that energy into the lower values, the low frequency components. So, ideally I would probably use a KL transform and show that I can squeeze in the maximum information in terms of the frequency domain representation in minimum number of samples. But DCT does a great job if the input image is correlated. On the other hand, if I have a computer generated image which is totally uncorrelated, the pixels are not correlated, then numbers will be all over the place here in DCT. But since we are dealing with real world images, we are able to focus and lead to maximum coefficients here, and here all the coefficients become small, so small that they tend to 0. Now, this critical observation will go a long way in compressing your image. Okay. So, let us see how DCT is applied. So, the first step is that you take an image and you do not work with the whole image at a time. You first divide the image into blocks. So, these could be 8 cross 8 or 16 cross 16 or 32 cross 32, but let us just focus on 8 cross 8 blocks. Why do we divide? Well, if you take small blocks of 8 cross 8, you have much higher correlation, and this correlation will play a critical role in compression. It goes without saying, higher the correlation, the fewer number of bits are required to represent that block, right. So, if we go back, if the image is 256 by 256 pixels in size, we break it up into 32 by 32 square blocks of 8 by 8 pixels and treat each one of them independently. So, if this was 256, then I would have 1, 2, 3 up to 32, 1, 2, 3 up to 32. So, this will basically decide my sub block size. Now, we only deal with one 8 by 8 block at a time. So, this is where we start, and the first step of course is to take a DCT. So, this will also result in an 8 cross 8 DCT samples, with the first one is the DC coefficient. So, we have taken a DCT here. Now, what we observe is that first few coefficients have some larger values, but as we go along they are extremely close to 0. Let us look at an example here. This is a toy example. I have not taken a block 8 by 8, but I have taken a 4 by 4 block, and for a real world image, if you do a DCT, these are the typical values you may encounter. So, let us go through this example. The first one is the DC coefficient, rest all are AC coefficients. This one is just the average. So, for 4.32 is average of the 4 cross 4 sized spatial image that we took. Rest all, as you can see, keep decreasing, and as we go to the really high frequency part, there is very little value here. Okay. So, now what do we do? What JPEG compression standard suggests is take that, and first step is to quantize. I am going to do lossy compression. I am going to throw away things. What am I going to throw away? From this 4.32, I threw away 0.32. For this 3.12, I threw away 0.12. For this 3.01, I threw away 0.01. This is just a toy example. I can choose how much to throw away, but I have quantized it. So, I get from this really 4.32, 3.12, 3.01 kind of a table, I get 4, 3, 3, 2, 3, 2, 2 and so on. So, then I make another observation that this end is low low, this end is low high, high low, high high in terms of frequency. So, the frequency gradually increases as we move away from the center. So, we perform something called as a zigzag coding, where I go zigzag, and this is the path we follow to encode. So, we do not do this raster line by line and line by line, because this gradually decreases 4, 3, 3, 2 jumps, 3, 2, 2, 2 jumps, 0, 0, 2. So, does not make sense. So, we do this zigzag encoding, and what does it lead? Well, if I read out the numbers 4, 3, 3, 2, 2, 2, so I get this 4, 3, 3, suddenly I start seeing runs. Okay? The moment I see a run, I am likely to do my run length coding, and this 3 3s or 3 2s will not really give me the compression. But what is amazing is this lot of these AC coefficients have become zeros, thanks to DCT, which packed all the energy into the first few coefficients, rest all is zeros. So, I have huge runs of zeros here, 0 0 0 0 0 0, and efficiently I can do my run length coding here. Please remember, we are not talking about the whole image, we are only talking about a sub block. Now, we do this same thing with all of them. Now, please note, it is not just one block. So, if you look at your image, which you broke it up into blocks. Now, let us take block 1 and block 2. So, let us consider these two blocks, because these two blocks are close to each other and their average values are likely to be similar. So, let us just write down the DCT coefficients of block 1 and block 2 which are adjacent. Now, the DC coefficient, the first box, please remember this is in the spatial transform domain. It represents the average value, this represents the average value of the next one. They are quite close to each other. In fact, if you take the delta, it is a very small number. So, we do the differential coding between these two. What is differential coding? Well, what you do is you find the difference, and I do this for blocks 2 and 3, blocks 3 and 4, 4 and 5 and all the neighboring blocks. If we now just do an analysis, if we plot on the x axis the delta x, which is the difference between these two values, and the histogram, the probability measure of sorts, and then we see a distribution that is very close to 0. We see lot of samples, which is not surprising because they do not change drastically. But as we move away from 0, the probabilities change. The moment we have a distribution, we should be able to do Huffman coding. You give me symbols or samples with different probabilities associated with that, and of course, I will do Huffman coding. So, differential coding plus Huffman coding, or differential encoding or arithmetic coding, because we have learnt both of them, and we should be able to deliver a much higher level of compression. All right. So, we would like to now summarize what we have done in today's class. We started our discussion with the design of Optimum Quantizer, which minimizes a predefined distortion function. We took an example of mean square error distortion. Once you get that distortion measure and you minimize it, you end up with the quantization levels. Now, if your input amplitude, which is a continuous random variable, it has a probability distribution. Based on that, we associate probabilities with the different levels of the quantizer, and then we encode them using Huffman coding. So, no two levels of the quantizer would yield equal number of bits per simple. So, different samples require and will be represented by different number of bits depending upon what kind of Huffman coding we are doing. We then looked at entropy rate, okay, and then finally we discussed this application of source coding, which is JPEG compression. We looked at how Huffman coding or arithmetic coding or even run length coding together can be used to compress the image. So, that we also looked at some examples. That brings us to the end of today's module, and we will look at other aspects of source coding in the subsequent module.